this point, I'd like to deal with questions from the last session or two first thing, if we could. Any questions about the reading or the process or anything? Because I'm going to do a little bit of a review. So, okay, well, very good. We'll just continue on. So, a couple of housekeeping things. First of all, I think the first time out, I mentioned that there is a mail order company that only sells navigation-related stuff called Celestere. It's an online store, and they have sextants and sight reduction tables and almanacs and plotting tools and all of that stuff. Anyway, and they're probably the best purveyors of sextants, actually, that I know of. And anyway, they generously agreed to extend a 10% discount on any and all the stuff you buy from them. You just go onto their website and type in the code MMSD, you get a discount. So I thought that was nice. If you were to buy a really expensive sextant, that might amount to quite a bit of money, actually. So it's a nice thing to have.
What's the website?
It's called Celestere, Celestaire, Celestere. And the code is MMSD. Okay. A couple things just to go back and review a few things before we get into the history part of it today. So I just want to emphasize when we were the session last time, we went through a long description of coastwise navigation. Part of it is just to review for those of you who've done a lot of coastwise navigation, just to have it again. Some of you who haven't done it, you've got a little bit of a review of it, but was really to get you to the place where we need to be to start doing celestial navigation, things like plotting and bearings and such. And in coastwise navigation, where a primary instrument is the compass, and we're using the Earth's magnetic field, that's where we went into the issue between the true direction, how it's influenced by magnetic variation, because the magnetic field, that gets you the magnetic direction, how that's influenced by the ship's own magnetic field through deviation, and that gets you to compass, okay? So going back and forth, where you add or subtract, we're not going to be doing a lot of that here. We're mostly just working with true, okay? That's the main thing that we'll be focusing on. So don't get too worried about the magnetic and doing the calculations to go back and forth from one to the other, because you won't be doing much of it. We also use the compass in reference to being a critical phase in history when people got their hands on this thing and began to use it for important stuff, but they didn't know why it worked or what it was causing it to work, and that doesn't happen much in history, really. So that made it a pretty interesting moment in time. So that's one thing, the true and magnetic aspect. I'm going to talk a little bit about also time. Most of us are regulating our lives by the local time, which is currently daylight savings, local mean time, or LMT. But for doing all of the figuring out for celestial navigation, it's universal time or Greenwich Mean Time, GMT. So how do you go from one to the other? Well, we're in a time zone now because of daylight savings that we're going to call +7. So if you want to know what the GMT is, if your watch is accurate, add 7 hours to it, and you get the GMT. Once daylight savings is over, we'll be in the +8 time zone, okay? So that shifts over with daylight savings coming and going.
But it was UTC was the one, because GMT is, there's like BST also, right?
Yeah, I don't know what BST is, but they're used, universal time and Greenwich Mean Time are interchangeable.
Okay.
But Greenwich Mean Time is the one most frequently used when you're talking about navigation, as opposed to other things. So that's what we're working with. And again, add 8 to your watch if it's accurate, and that's where you're at. That's what time it is. So knowing that is important. Then there's a possibility of getting confused, because when we're talking about degrees of the circle, we've got degrees and minutes and seconds. We don't use seconds very much when we talk about the circle, but we do use minutes all the time. We use degrees, minutes, and tenths of a minute typically when we're working out these sites. On the other hand, when you're taking the time, you've got hours and minutes and seconds, right? Well, time, and they do relate to each other, because the Earth is a clock, it's a machine, it's moving around, and it goes around once, as we know, every 24 hours. So in 24 hours, it goes around 360 degrees. So you are frequently in doing this stuff, converting arc to time, and that's really is how fast is the Earth moving as it rotates on its axes. So if the Earth rotates 24 hours, if the Earth rotates 360 degrees in 24 hours, it is moving 15 degrees each hour, isn't it? It's moving 1 degree every 4 minutes, okay? So you're going to be doing these going back and forth arc to time calculations occasionally, particularly in predicting the noon sight. And that's the main one you're going to be using it for. But understanding that not to get confused, we're not talking about, well, we won't be dealing with seconds when we're talking about altitude of a body or a compass course or something like that. It's degrees, minutes, and tenths of a minute. Also in latitude and longitude, it's degrees, minutes, and tenths of a minute. It used to be seconds. We're not using that. And time, it's hours, minutes, and seconds. Okay, and you can readily convert from one to the other on that ratio. All right. Okay. What we're going to do today after this, we are going to talk about. We're going to do another story, and give you a little bit of background on that. I'm going to warn you that I jump around in time in these stories, right? Because I try and relate them to whatever the subject matter is at hand. So there is a bit of that, and sometimes there's a little bit of repetition too. But just to be warned on, tonight's isn't going to be very long, really. The first part of it, it's not really a story, it's just a little bit of a review of what we've done. We're going to talk a little bit about the sextant, how to read it and how to correct it. And then we're going to go into the history, and it won't take too long. But then we're going to focus on the process. That's what you've been reading about in the Kittredge book, is the process of doing this. He has 10 steps. I've pared that down to 9. So what we're going to go through is go through the process, what each of the steps are. We're going to go through it again, and then we're going to relate where in each of those, how each of those steps relate to one of these two books, the Nautical Almanac and the Sight Reduction Table, and how they're organized in doing that process. Okay? So we'll go through that relating to the books. And then we're going to do a problem, okay? An actual sun sight that was taken this last weekend. Actually, a pair of them. I'm just going to go through it once, and about the time we get to the end of it will be when your eyes all glaze over, probably. And then we'll go through it once more. After that, what I want you guys to do, because you practice looking through a sextant, I want you to go and try and take a sight sometime during the week, between this week and the next, okay? A good spot to do that would be the Coronado Beach is a good spot, anytime after noon or so, because it curves. In fact, even at noon, you can look due south. Point Loma might be good, but your height of eye of Point Loma is pretty high, actually. But go there if you want. What you really need is a nice clean horizon with directly below the sun. So, and that would happen in Coronado anytime in the afternoon. So that would be a good spot to do it. But if you don't have that, again, there are alternatives to it. If you can't get a shot at the horizon at all, well, you can put some sort of highly reflective fluid into a pan, and then bring the image of the sun down onto its reflection in whatever the liquid is. The northern explorers used mercury. You can use old motor oil from the last time you changed your oil in the driveway. Anyway, bring it down and then cut the angle in half, and that will give you pretty much altitude. David?
There's also a really good place in La Jolla, right between La Jolla and Bird Rock. You can find it in Google Maps by searching for Vista Point.
Vista Point, okay.
There's a different place called Vista Point. This is in La Jolla. It's very nice.
Okay, cool.
Perfect view of the southern horizon, easy to get to.
So it projects out a little bit in that regard, yeah.
Yeah. Right between La Jolla and Bird Rock.
Okay, that's good to know, everybody. So you're right, Bird Rock area, Vista Point. And can you find Vista Point like on Google Maps and stuff? Will it direct you to it?
Vista Point, there are several different places called Vista Point. You want the one that's in La Jolla. It's on something La Cañada, I think.
Okay, everybody get that? So there's another good place to get sights from.
Do we want to be facing south during our...
Well, in the sun's going to move over to the west progressively and just continue moving. It will be due south at noon, at astronomical noon. I'm not sure where that lines up exactly with actual time noon, but if you got out there and started taking shots at noon and then took 2 or 3 over the next 2 or 3 hours, And by the time you've done with second or third, you will have a group of followers around you wondering what you're doing and what's going on. And you'll have your own miniature class going on. That's usually what people find. So, okay. All right. Okay, so let's go through this a bit. All right. So I'm going to do a little bit of a review. So again, you can plot on your universal plotting sheet, or you can plot on this map that y'all got from San Diego to Santa Rosa Island. Either one. The plotting sheet you're going to need to use when you go sailing across an ocean, because it would just be very uneconomical to spend lots of money buying accurate charts of empty pieces of ocean. So you can make and the exercise of making your own chart using plotting sheet is useful for that. It's also useful to understand just how Mercator projection works and how charts are made. So to review that once again, we start off with this, this sheet. It's got lines of latitude going across it. Those could be any latitude you want them to be. You're just going to label them. And it's got one single line of longitude going down, and it's got a compass rose. Okay, and in the lower right, it's got an interpolation scale so you can interpret minutes, not just degrees. Okay, located along the right side of the map, or in the middle part, excuse me, are minutes of latitude. Okay, and each one being 1 nautical mile. Okay, so to turn this into a Mercator projection, you first of all start off by deciding what latitude you're going to be sailing at, and we have just labeled this one here with 33 degrees as our mid-latitude. Okay, if that's where we're at already, then that's a pretty good choice, but you've got a span of 4 full degrees of latitude, or about 240 miles from top to bottom, until you sail off this map and have to go into another one. So, so you might want to gauge the direction you're sailing in. If you were headed southwest, you might want to make that 33 degrees at the top and work your way down, because you'd be able to stay on this page for longer. But whatever the case, we've got 33 degrees, and so now we need to know how far apart the lines of longitude are. So there's several ways to do that, but a way that you could do it, actually, if you didn't have this fancy plotting sheet, you just have a piece of paper, is take a protractor and make your lines of latitude the width of the protractor, and then just draw a line up. And then that line, where it touches the edge of the circle, is where your first line of longitude would be. In this case, you can have it go through, it's 33 degrees up, that upside, and when you line it up, it also cuts through 33 degrees on the bottom side, and they should be parallel. So that gets the spread of longitude lines at the proper distance apart. As you see, it doesn't touch the edge of the compass as it would be if you were at 0 degrees latitude. You get this one, and then you go and you get the distance with your dividers, and then you mark where the other lines of longitude are going to be, and you draw those in, and now you have a Mercator projection of the piece of ocean that you're going to be sailing on. Okay? And if you don't want to do that, you can just use the chart that this piece of paper is sitting on in this image. Okay, and then of course the last thing you want to do is label those lines of longitude in accordance with where you think you'll be sailing. All right? Okay, now what I'm going to do is I'm going to pass around a handout. Okay. That one. And I see my take one and just pass it around back there. So what I'm passing out is a handout and so forth were elements of their cosmology and their spiritual system. And they understood it that way, and they understood it as a religious exercise, and one in which there were certain things you did and didn't do, there were certain things that you constantly were aware of, and your vision of the world, your cosmology, was as though the canoe was at the center of the universe. So it's the ultimate Ptolemaic system. In fact, the way they described it is, it was the role of the navigator through will and consciousness to repel the island that they just left and draw towards them the island they were sailing to. And that was actually a very accurate reflection, based upon it was validating a system of wayfinding and cosmology that actually was internally consistent. Now that sounds far-fetched, but what we're going to see, I think, is maybe not so much. And certainly we have seen a rise in that in the ancient world, and then it falling away, and then the rise of it again in the early modern era and the Enlightenment. So if we go back to a map like this, this is something a little bit more like what Tupaia would have been able to respond to. It was the world depicted as medieval Christians saw it. This is again another TO map. Jerusalem is at the center of the world because that was the centerpiece for the Christ story. For Tupaia, the center of the world in a land center, if it wasn't the canoe, was the sacred marae at Tapu Tapu Atea on the island of Raiatea. The island of Raiatea, the other Tahitian name for it is Hawaii, which is the word for home. And it's where it was the origin of all navigation throughout the Polynesian world, or all spiritual wayfinding throughout the Polynesian world. The Christian worldview was a bit different though, because whereas the Polynesian worldview was outgoing and extroverted and let's sail off and voyage to far distant places, the Europeans at the time this map was made weren't all that keen on that sort of thing. Europe had been in decline for a long time, and it had recently had some really bad setbacks, including the fall of Constantinople. Well, I say recently, to the early modern era. This map was produced in the 13th century, so it was produced before Constantinople fell. And it was produced before the bouts of Black Plague that washed over Europe beginning in the 14th century, and then recurred every generation or so. So it hadn't had those disasters yet, but it was still had been in decline, and the European worldview was fairly introverted, and the notion of the ocean sea beyond the known world was pretty frightening. And they also had the impression that if you went out into the world any direction other than east, and east was towards the direction of the Garden of Eden, so that was possibly safe. East is up on this map, as it is on most TO maps, and you can see, God there presiding over the east of the Garden of Eden. Home, I guess, right? The equivalent of Hawaii for a Polynesian. Anyway, if you went other directions, the world you encountered was progressively more frightening, hostile, savage, and bizarre. And so were the people in it. So there wasn't much to look forward to if you were going to go on walkabout, and go out exploring. You would encounter all sorts of bizarre and strange individuals. In fact, on this map, there's even a bestiary. I've got a large version of it here, in which there are enumerated a good assortment of all the crazy kinds of critters and people that you would encounter if you went out on one of these forays and you got yourself too far away from the center of the Christian world. Bestiaries were very popular. They captured people's imaginations. They persisted all the way into the 18th century. This is a bestiary from, let's see, this is in the early 15th century or late 14th century. And it names all the different kinds of bizarre creatures there. There's a guy called a monoped who just has one giant foot, and he hops along until he gets tired, and he lays on his back, puts a foot up in the air, and sleeps under the shade. Right? There's another character without a head, but a face on his chest. There's another character with 6 arms, so someone had probably seen a statue of Shiva somewhere, I think. And all of these characters are the inhabitants and denizens of all of these places. But there was one place more frightening than others to go to, and that was depicted in this map here in 1542 by a cartographer named Sebastian Munster. We have one of his maps down below in the exhibit. And if you look at the ocean as it's depicted here, it's not it doesn't look nearly as pleasant as it does to go out there. It's just really a horrendous looking place. I mean, you have sea monsters wrapping themselves around ships. You have, a whaling ship throwing their whale oil overboard to placate the angry whales that they've irritated. You've got gigantic lobsters snapping people in half. It's just really, really a scary place. The message of this is, don't go there, this could happen to you, all right? If you look at the upper part of this, though, it's on the land as it's depicted. It's all very safe looking. People are planting and they're doing their farming, and the animals are all nice and cute, and everything looks just fine. So, of course, the moral of the story is, don't go out there. And that story had been, that had been promulgated for quite some time, and Europeans had been cautioned against going out to sea because it was so threatening for a long time. It was based on generations of seafarers. Some of them, those were in theological texts, and some of them were, stories like the story of this guy, Saint Brendan of Clonford, Brendan the Navigator. He lived in the 6th century, but the book Navigatio Redondas was published in in the 8th century, actually. So it was sometime between the time these supposed voyages. But Brendan was an Irish monk who set out to sail west in a currach, or a leather boat, and that voyage was replicated by a guy named Tim Severn, who just passed away a couple years ago, in a leather boat, and was a really sort of a National Geographic cover story for a while. Anyway, in the story of St. Brendan, in this particular episode, they're at sea, they've been out of sight of land for a long time, they don't know where they are. They see an island, and they said, well, we should hold mass, because these are all monks. So they pull the boat up onto the island, and they get out all of the mass stuff, and they start to hold mass and pray, and the island starts to move. It turns out they have just beached their boat and conducted a religious ceremony on a whale, okay? But it is no ordinary whale. This particular whale was pretty smart, and he engaged all the monks in a debate on the fine points of Christian theology. Right? So again, interesting and magical people, magical things that could be found out there. Not all of them were terribly scary. But efforts to rationalize that space had lasted for a long time, and particularly the relationship between going to sea and either staying along the shoreline or going out of sight of land, that relationship between that and astronomy. Now, why would that be the case? Why would astronomy really start to figure from even ancient times into navigation? Anybody have any thoughts on that? I'm sorry? Right? Stuff in the sky, that's all you can see. So you've been deprived of everything else, so you go with the stuff in the sky. So at an early date, and institutionally, trying to somehow figure out in a precise way where all the things in the sky were, to use them as reference points, began to be something of an urgent project. And it had reached I guess a really important waypoint in the 4th century BC with Alexandria. It was founded by one of Alexander's generals, General Ptolemy, and it was ruled over up until Cleopatra, who was the last of them. But it was institutionally, it was one of the most advanced places of its time. It sat at the confluence of several trading routes up the Nile, the trade route over from China, the Eastern Mediterranean, and as a result, they were at the nexus of all kinds of opportunities for trade and also encounters with people from other places. So there were several things that was noteworthy for. One of them was the Pharos, or the Great Lighthouse, that was thought of as one of the wonders of the ancient world. Another was the Great Library at Alexandria, which was the first library probably in history to have over 1 million volumes. And it had that until it burned down in about the 1st century BC, built it again, it burned down again about 300 years later, and then finally in the 7th century AD, it burned down for the last time. I suppose there is a library now, but they probably don't put much stock in it because they keep burning down. Anyway, it was a centerpiece of learning, and Alexandria also had a great astronomical observatory, medical school, research labs, and so forth. And it also had an institution called the Museum of Alexandria, and it was ruled over by scholars who were actually political leaders and actually wielded quite a lot of power in Alexandria. And among them, some of them were the foremost names in the development of navigation, including Eratosthenes and Hipparchus and Posidonius. Anyway, this was an institutional effort to actually bring the things up in the sky down to where mariners could use them, because this was a place where seafaring was one of the center points of seafaring in the world. And this effort did continue. It had its rise and fall over time. But in the 2nd century AD, Claudius Ptolemaeus, also known as Ptolemy, but not directly related, I don't think, to the Ptolemies who were rulers, concocted an organizational scheme for all the things you saw in the sky. Prior to that, the Greeks had imagined that the Earth was the center of the universe, and that all the things in the sky were attached to a series of concentric crystalline spheres. The reason you didn't see them is because they were transparent, but all these things were attached to them and would rotate around to different degrees, but they never got terribly precise about it, really, until Ptolemy came along, Ptolemaeus, and began to actually look at these things in predictive ways. And that became the version of the solar system and the cosmos ultimately accepted and then endorsed and then enforced by the Catholic Church. To say that it was any other way would have gotten you in trouble at some point. So Earth at the center of the universe, followed by all of these other things going around. And that Earth-centered universe is actually, we don't recognize it as what we think the solar system looks like, but it's actually the one we use more or less in doing celestial navigation. And it is the one that Cabrillo used. He had no knowledge of any others when he set out to discover the part of the coastline that we live in now. So, let's see, I got these kind of out of order. Okay, let me do this earlier today. So the first contradiction to Ptolemy, and the first person to challenge the Catholic Church, he probably had a good judgment to write a contrary view and then die right away before they could do anything to him, was a Polish astronomer and theologian named Nicholas Copernicus. And he postulated a heliocentric universe where the sun was at the center of the solar system and everything else revolved around it. Now, his reason for doing so has often been said, well, it was one of the earliest scientists of the day. But his reasoning for doing this wasn't because it matched observed phenomenon. There was no observable difference between Ptolemy's system and his. The reason why he wanted to chuck Ptolemy's system was because he thought it was monstrous, because over time, to account for all the various movements, retrograde motions, and other things caused by the planets and so forth, you had to have this incredibly elaborate system with cycles and epicycles and contrary cycles and everything else that was enormously complex. And Copernicus, who was a theologian also, just said, God would not have been so stupid as to make anything this difficult. So I just don't believe it. That's all there is to it. And so he concocted a completely different system, not because the observations matched it, but because he just thought it was more cool than what Ptolemy had done. And wrote it up and then died. But right away, people started to buy into it. And interestingly enough, one of the most important books of the 20th century, written by a guy named T.S. Kuhn, who wrote a book called Copernican Revolution, based on this guy, and then another one called The Structure of Scientific Revolutions, described the process of science as politics by other means. In other words, it isn't this endless search for truth, or it hasn't been. What happens is, have you heard the word paradigm? T.S. Kuhn invented that. A paradigm is a worldview. It's a belief in a whole system that is eternally consistent. People buy into it, and scientists buy into it. And what happens is not somewhat in the gradual search for truth, there's a better evolving vision. What happens is that everybody who's bought into that paradigm dies. And everybody who wants to make a name for themselves comes up with another paradigm. And then that soon becomes another paradigm, and the same cycle repeats over and over again. So actually, in a way, what people believe about science often has had more to do with politics and theology and emotion, and often than it has by clear-cut observation. So Copernicus, doing this, launched a series of astronomers who began to try and come up with an ever better notion for this. Tycho Brahe, his claim to fame was that he had the world's most accurate instruments. And so with more accurate instruments, he felt he could produce a version of this more useful to navigators and just more useful all around. And it was kind of a blending of the Copernicans and the Ptolemaic systems. But he could just, it just didn't work either. And it was not as complex as the full-bore Ptolemaic system, but not as simple as was Copernicus's either. So the next guy along was really interesting, Johannes Kepler, who was a German astronomer and a friend of Tycho Brahe, who was Danish. Anyway, Johannes Kepler was convinced that it was a Copernican system, but it wasn't going to be just that, because God would not have just thrown this stuff out there without some sort of master plan in place. And so he had several versions of why these planets were at different places and what they're supposed to do. And he came up with the notion of the planetary solids, so that you had, some of the celestial bodies were on this sphere, inside of which was a square, was a cube, inside of which was another sphere, inside of which was a dodecahedron, inside of which was another set. Every single planet, every single thing out there that you could see was attached to one of these Platonic solids that defined its orbit and defined the distance of one thing to another. The problem with, though, it just didn't work. It was frustrating to no end, and he had access to Tycho Brahe's instruments, and he just couldn't make that work. So he came up with another idea, and he thought that was okay. He was also interested in music, and he thought, it's harmonic chords. That's what's determining the orbits of all the planets and everything. It has to do with music. God would have composed a symphony for us. He wouldn't have just stuck things out there. And so, if you've heard the phrase, the music of the spheres, okay, it comes from Kepler's notion. And so I guess there is a music of the spheres, and he just couldn't get to sound very good, I guess. In any case, it didn't catch on, whatever. What he did do, almost by accident, he just said there's some organizational scheme out there by which we can predict these things. So I thought, okay, and he started looking into it, and he determined there were these three things that were always true about all the observable things in the solar system. First of all the planets, they don't move in circles, they move in an ellipse, okay? And in the ellipse, there's the thing that's moving around, like the sun, is at one foci of the ellipse. And the other foci, there's just nothing there. Now that goes back into the kind of the monstrous thing that Copernicus didn't like about Ptolemy. But so why is the planet revolving around one thing that's there and one thing that isn't? But it was, for some reason. So anyway, that was his first observation, his first law of planetary motion. These are all ellipses. Secondly, he determined that every single planet, this was true, a line connecting the planet to the sun, an imaginary line, okay, and you look at the line as it moves over around the ellipse, as the planet is moving around its orbit, in equal amounts of time, the areas swept by that line are always equal. So, when the planet gets close in to the foci around the sun, it's moving really fast. Okay, so it's sweeping a big area, and it gets further away, it slows way down. So it's equal areas and equal amounts of time. Why? In Kepler's mind, well, that's God's idea. I knew there was an idea, and this proves it. God has actually decided this stuff. And finally, what was really elegant is that the square of the orbital period equals the cube of the semi-major axis of the orbit, or the average of that. Okay, the square of one thing is the cube of another, so it's all mathematical, all fits in, so God is safely back at the top of creation. And there you go. So as you see, some of these things, even though these guys are all waypoints in the history of science, they're all motivated by trying to make something work in accordance with their own cosmology and their own belief. And maybe they're not so far removed from the TO map. And then you have I should say also, Kepler was heavily influenced by William Gilbert. Now, I mentioned to you that the compass was the first thing the first instrument that people were using that measured an aspect of nature that they couldn't sense. And then not only that, it was moving to some sort of power that they didn't understand. And there was no theory about what it was for a long time, until this guy, William Gilbert, came along, and he basically described this force called magnetism, but he described it as the soul of the planet, the soul of the Earth. And the soul of the Earth is capturing the moon and forcing it to move. And the soul of the Earth is what is causing the needle in the compass to go in a certain way, that the Earth is kind of a living thing. Question?
Yeah, if they didn't know what it was, where did it come from? A piece of metal and water one day, or?
You mean the compass?
Yeah.
Well, somebody observed that you could take this rock called a lodestone, and you could rub it on a piece of metal, and it would line up somehow pointing kind of north. The Chinese discovered it first, and then it moved along to the rest of the world. As to who was the first person, no, I don't really know who did that, but it was some Chinese guy, But still nobody knew what it was, and the Chinese didn't have a theory either. But Gilbert said, well, okay, the Earth has a soul, and planets have a soul, and that's these things are all moving to that. And in this picture here, you've got Gilbert showing his experiments of magnetism and stuff to Queen Elizabeth, and you've got his counterpart to the lower right, John Dee, who was a leading scientist of his age, but always referred to himself as a wizard and a magician. So these things do kind of interrelate with each other. Okay, well, all of these things are showing define the movements of these things in the sky. On one hand, because they want to, they want to make them useful. And in doing so, they have to actually take subjective observations and turn them into objective observations. So Brahe had his instruments. Kepler was trying to mathematize or geometricize the movements of all these things. An inherent belief that you could reduce everything down to a set of laws and into mathematic principles. Now, for a long time, before there were charts, navigation was done by rudders. That's a shortening of the French word routiers. The first ones we know of were called the Periplus of Skylax. That was the 4th or 5th century BC. And another one that we know of and we have references to are the Periplus of the Eleutherian Sea, which is the Red Sea and Indian Ocean, from about 60 AD. They were relative reference texts. They told you could sail along a certain course at a certain time and what to look out for, but what you were actually seeing when you were sailing along the coastline. If you didn't have a chart, that was your key. And gradually over time, with the advent of charts, that became more and more sort of rational and mathematical, which you see this evolution for. I think I showed you that slide last time. You get a sense of the space people are moving through, that space can be defined by numbers and by sailing compass courses. And those compass courses ultimately evolved from a different form of direction, as is thought of in the Mediterranean. This is a Ptolemaic version of the Earth, showing the different winds, and the different winds would tell you the direction to sail and so forth. The mariner's compass is an 8-point compass, whereas the compass of the winds is a 12-point compass. If you go to Athens, the Tower of the Winds, it's a Roman building in Athens, but it's a 12-sided building. So with the advent of the compass and the advent of this abstraction of direction, you then can start to use it for things, to navigate. And the first known reference to the compass in the West is by Alexander Neckham in 1187. There's references to mariners being able to use the compass in the 1200s, and then the Carta de Zana is from about 1270 or so. So the compass preceded it, and the oldest known compass we have dates to about 1426. Okay, so now you have location and now you have direction, and they decided to use the 360-degree circle, which was originally Sumerian. The Babylonians picked it up, and then the Greeks picked it up from the Babylonians. So that's the circle divided into 360 degrees. In terms of distance, or length, one of the most basic navigational instruments of all, in history, is the lead line. Or in this case, in this Egyptian drawing here, a sounding rod that they just stick down and poke down at the bottom. You can tell how deep it was. Lead lines were used all the time in the ancient world, and the medieval world. This wood cut, I think, is from about I think it's from the 15th century. So lead lines were used to determine the depths of the water, and of course that was measuring something you could sense because you could pull it up, and the distance that you would pull it up with an outstretched arm for most people is about 6 feet. Hence the fathom became a basic unit of measure. Okay, but there were other units of measure as well. They used different ones in ancient Egypt. In English use, maritime use until the end of the 16th century, the common thing that people used wasn't a nautical mile at all. It was called a kinning. Okay, how many kinnings was it? A kinning is the difference that you can see on a nice clear day from the deck of a ship about 10 feet high, which I think is about, 3 or 4 miles, 4 or 5 miles, something like that. So they would talk about the distance between places and the number of kinnings. The French we use the same thing called views. I'm sorry, 20 miles. I should have said 20 miles. Misread that. The French view was 14 miles. The English kinning was about 20. Also, what you found in those rudders were just a day's sail. Obviously, if the wind's pretty strong, it's going to be a different day's sail than if it's a dead calm, but it was pretty much a day's sail. And the distance, of course, always related to speed. Ultimately, when you settled on a nautical mile and a minute of latitude, when these things got regularized, then speed and distance became sort of norms that people used all the time. And with that, to measure speed, they began to use things like chip logs, particularly after you have widespread acceptance of a minute of latitude equals a nautical mile. Okay, something on the Earth. There was a lot of differences of opinion about how far a minute of latitude was, but we more or less settled on more or less what we have now by the late 17th century. And people began to be more precise then in measuring these things with things like the chip log here, which we have examples of again down in the exhibit. The earliest reference to using something like this to measure speed was William Bourne's treatise on navigation. He was a contemporary of Drake, which he wrote in 1574, called A Regiment of the Sea. And the way you use this thing is you had a drogue that was triangular and it had a little peg. If you pull the line, it pulled the peg out, and it went from being a drogue to being just this flat plate. You threw it over the side, you turned the sand glass up, and you count the number of knots that spin out over the reel. And 1 knot equals 1 nautical mile per hour. That's why you say you're going at so many knots. Until that, people just threw a piece of something floating over the bow of the ship and counted the number of heartbeats it took until it went by. So that's how Columbus determined speed. But this was a more precise method than ultimately, beginning in the late 1800s, people began to use what were called Walker logs or taffrail logs. And that was a torpedo-shaped device that would tow behind the boat on a braided line, and it would spin around, and that would just record the number of nautical miles you went, and you would look at that. When you hove one of these taffrail logs, it was typically at the end of your half-hour watch. And then if you might write it down, or if you were the mate of the watch and you were illiterate, you had this device called a Travis board, which we have one down there, and it had 2 sections on it. There were a series of pegs, and there were 8 lines of holes, and there were 8 lines of holes going out from the center on kind of compass rose. I wish I should have had a picture of it. But in any case, you would then, for each half hour of the watch, take 1 peg, and for the first half hour, put it on the course that you steered, and the distance you think you went on the lower part. At the end of it, you just handed this thing over to the guy who was doing the navigating. You didn't have to write, and he would look at it and be able to tell how far the ship went during that 4-hour watch. So it was just a way of keeping track. Something similar to that, we have one of those down there. We also have the deck slate from navigating the Star of India back in the 19th century, which is not too far away from it. I don't know how many of you have seen that before, but it is from this ship. So similar kind of a thing. Okay, so far as location, you need this reference system if you're going to bring everything within this common field. And efforts to make those consistent go a long way back. This is an image of a Greek klimata. That is an attempt to organize or describe latitude in accordance with actual climate. Okay, and there was a belief that if you went too far south, it would be really dangerous because the pitch in the ship's hull would melt and the ship would fall apart or would burn up or something like that. So the Greeks didn't really fancy going too far south because it seemed dangerous to them. But nonetheless, it was an effort to try and establish latitude, at least initially, as the primary consideration. We think of latitude, as we do of longitude, of things that are regularly spaced. But in the first iterations, like this iteration of the Greek world, they weren't. The lines of longitude weren't evenly spaced around the circle. They went through important places, right? So if you were Alexandria, you had a line of latitude, a line of longitude going through your city. Likewise, lines of latitude. So it was an attempt to systematize location, but it was still pretty subjective and based upon, not upon some regular array, but on people's understanding of what was important and what wasn't. So the efforts of all of this gradually, though, became to standardize to be able to generate a set of documents that would have all the world in it, and it would be able to be very useful to conduct trade or warfare or anything else. It was something of high commercial and high military value. So when the age of exploration began, and European states began to develop oceanic capacities, and those became pathways to empire and wealth and power, right away the effort to try and control that information, not only make it accurate and useful, but to keep other people from having it, became a high priority. So the first true institutions having to do with navigation in the age of exploration were these two, the Casa de India, and this is a picture of Ribera palace in Lisbon was founded by King Manuel I of Portugal in 1497. And then the Casa Contratación in Sevilla, founded by Isabella I in 1503. It's actually, the Casa de Contratación was not ever in a building, it was spread out a bit. But all the stuff it generated is today in the Archive of the Indies in Sevilla, and that's a picture of the Archive of the Indies. So the creation of these institutions was an attempt by nation states to embrace navigation as an element of statehood, to control it and use it as a way of enlarging and also protecting empire by keeping this knowledge secret at all costs. It was actually a death sentence if you gave this stuff away. If you were a pilot in Portuguese or Spanish service, you were required to turn in your logs, your instruments, your charts, everything used to navigate ships at the end of a voyage. It goes back into the Casa de Contratación or the Casa de India, and there it stays. You would think it would all still be there, but apparently some stuff has disappeared over the years because it was really valuable. So for instance, the Piloto Mayor of the Casa de Contratación in the 16th century, Sebastian Cabot, ran away with a lot of information and used it to buy himself a really nice life and a knighthood in London, okay? And because he showed up in London with all of this classified information, which was of immense value. And it contained possibly the only Spanish version of the Carte Patron, the master map of the entire world. That was at the time the most secret document on Earth. There's the thing he stole, there is no known copy of it in existence today. For the Portuguese version of the Padrón Real, there's this, what's called the Cantino chart. In 1502, it was stolen from the Casa de India for the Duke of Ferreira by a guy named Cantino. And it's interesting because it shows, going down the middle, the line of demarcation established by Alexander VI in 1492. And then I think this one has it, it's got it moved 240 leagues to the west in 1494. Okay, so this map was stolen in 1502, and you can see how Brazil this divides the world. Spain on that side, Portugal on this side. So Brazil is in the Portuguese sphere, isn't it? Which is why they speak Portuguese. Why everybody in this part of the world speaks Spanish and they speak Portuguese and so on. What's interesting about this map is that this was stolen in 1502. The voyage that established Brazil by Cabral was in 1504. So somebody got there before he did, but he's the guy that's giving the credit for it. And the Portuguese knew about it before that voyage. And he did seem evidently to know where he was going. So one thing about this line, there's several interesting things about this map and this line, even though it was kept highly secret, that's a line of longitude. It was the first line dividing power between two states ever that wasn't based on a shoreline or a mountain range or a river or some sort of feature on land. It was a line drawn across the ocean, and no one would know how to find that line for hundreds of years. And yet it determined the lives of millions of people. There were literally, at this time, 3/4 of the world's population didn't live in Europe. And yet their lives were, everything was divided between the only two states, European states that had oceanic capabilities. It didn't matter if they'd lived there for thousands of years, but overnight they became somebody else's property, essentially, as a result of that line drawn on that map. So you can see why it was so valuable, why it was held in many respects as close guard secret. I'm sorry?
Which boat was that?
Oh, Alexander VI.
About what year was that?
Oh, that was the initial the decree was the Papal Bull was in 1492, and then the line was shifted 240 leagues, probably because the Portuguese wanted it that way, to the west. So it divided the world, which sets the stage for another thing to come up. That in 1494 defines that part of the world between Spain and Portugal. Well, the world is round. What about the other side of the world? There's another line, isn't there, that goes around it. And then the question becomes, okay, where are the East Indies? Which side of the line do they fall on? Is it on Spain's side, or is it on Portugal's side? Because whoever gets that is going to have the pathway to immense wealth beyond imagination. So how do you determine which is which? How do you know? The only way to know is to go there And who did they send? The Spanish sent a Portuguese navigator, right? Ferdinand Magellan. And so that's another story. We're not going to talk about that too much. But I am going to go into this one last thing. This is the only piece we know of. This is a Diego Ribeiro map from 1529, and it is a fragment of the Spanish Padrón Real, right? The highly secret world map on which all their empire was based. There was one big map, but it's speculated that the entire map was never allowed to exist is one thing. It had to be broken up and all the pieces kept in separate places so that no one could ever put it together and really figure everything out. So, good way of keeping things secret. And all based on navigation. But we're not so secretive these days, right? So it's open for everyone. Okay, that's the end of the story part. A question back there, yes?
Yeah, I was wondering, what about something like the Harry Reese map that was made in the Ottoman Empire?
Yeah, that gets often cited by Menzies, doesn't he? I don't really have much to say about that, really, to be honest with you. I've looked at images of it and so forth, but I'm not really sure of its provenance. So there you go. And likewise, there's also the famous Vinland map, right? Vinland map and the Ottoman relation, which pretty much was a fraud, even though Yale paid, I don't know, ungodly amount of sum for it back in the 1950s. Margaret? It's called a kenning, Kenning. Like the old phrase, I ken what you're saying, you know? I see what you're saying, right? So it's a line of sight thing. Okay, good questions. Any more questions? All righty, well, I'm done with the storytelling. So we're going to talk now about we're going to talk about actually doing all this mystical stuff and bringing harmony to the universe by doing so, right? So, as I told you, there's going to be 9 steps. Sound good? Oh, yes, question? Yeah, everybody go get a glass of water. We'll take a break. I could use one too, so I'll take a break also. See you back in 5 minutes. We just learned how to read the sextant. Your second step is to take that sextant number, which we're going to call an HS, and we're going to correct it into something called an HO, from the sextant altitude to an observed altitude. And you do it because, there might be all of these imperfections. The sextant itself might have an error. If you did, stars and planets are little pinpoints, but the moon and the sun have disks. So even though mathematically all this is figured out to the center, you're actually looking at the edge. So what did you shoot? Was it the moon or the sun? And did you shoot the lower or the upper edge of it, right? Okay, so that's one of the things that you would need to do. There's a correction that's combined with that, caused by the fact that for the light of a star or the sun to get to you, it's got to penetrate through the Earth's atmosphere. When it does, the lower it is, the more it refracts. If it's directly overhead, there's not a lot of refraction. But low down, that light is bent as it comes towards you. So that's a correction. And then, if you're high up in the air, it's further to the horizon. So that edge you're bringing the body down to, it's further away than if you're literally just 2 feet off the water's edge. So your height of eye is another thing as well. So there's all these things that you're doing to correct the sextant, as though your sextant were a perfect instrument, that you took a star sight with a perfect sextant on a planet with no atmosphere or something like that. Okay, then your third thing, and this is what this book is for, find the position of the sun. Okay, now I'm going to talk a little bit about that just now. One more time, I'm going to review what we talked about last time. I'm going to get up on the stage to do that. The position of the sun, we could use the words latitude and longitude, but latitude and longitude really only refer to the position of something on the Earth. But the spot right underneath the sun does have a latitude and a longitude, right? And that's called the GP. But up in the sky, it's got a different name. Okay, the longitude is called Greenwich hour angle, okay? And the latitude is called declination. So Greenwich hour angle goes all the way around, declination is north and south, okay? Now, the principle of what we're trying to do here, by finding that where the sun is, if you can imagine, if the sun is directly overhead, I'm standing in the shadow, my own shadow, aren't I? The sun's at 90 degrees. I actually am right, if I know what the sun's declination, its GHA is, I know where I am, right? If I have to be right under it. It's not very often that you're exactly under the sun. You have to be in the tropics for one thing, and for another you have to be there at the right time, and then it's only true for an instant anyway as it passes over. But for that instant, that can find your spot, right? So the sun's GP is the same as your latitude, longitude, and the celestial version of that is declination in Greenwich hour angle. Now, let's freeze time for a moment. I'm standing in my own shadow. If I walk over here, right, I'm not very far away, but I have made that angle, right, between dead horizontal to the horizon and the sun. Instead of being directly overhead, it's infinitesimally a little bit of an angle, right? So, okay, and that angle defines a circle around the GP, doesn't it? Everybody on that circle would see the sun at the same altitude, right? It would be 89 degrees, 59.9999999 minutes, okay? But nonetheless, it's a circle, and that circle is a line of position, right? So that's not happening any more often than it is when you're right on the sun's GP. But when you do shoot the sun, what you're doing is it's the equivalent of shooting that lighthouse, except it's way back there. And that line that you're on is a huge circle that goes around here that you draw on your plotting sheet as a line, and that's a line of position. So when we pick the moment, we shoot the sun, and we get that angle, we're trying to find that line, okay, that we're on, right? That was a point, and it's a small circle, but really most of the time, it's a big, huge circle. Is that all making sense about the objective here? Okay. So our process is involving doing that depends heavily on finding the position of the sun. Now, this book here, the Nautical Almanac, it covers two of these steps. First of all, in this first pages, and everybody ought to bring their Nautical Almanacs and stuff with them. In this first pages here, you've got what you need to do to correct the sextant. Okay? It's the page called Altitude Correction Table, Sun, Stars, and Planets. And so this leftmost column, if you open that book, says sun, and it's got the year divided into two halves, October to March and April to September. And then you need to know if it's the lower limb or the upper limb. That will give you what's called the main correction. All right? So we're still correcting the sextant now. And then to the right of the page, it's a dip, and that gives you the correction for your height of eye. So this very first page of Nautical Almanac helps you correct the sextant. Okay? Most of the rest of it involves in finding the position of things. So if you just turn to any page, you'll see the date, the year, and you'll see a date. It'll say, for instance, if we go to what's today? Today's the 22nd, 23rd? Oh, see how behind the times I am. Today's the 24th. So if we turn to the 24th, that's Tuesday, Wednesday, Thursday. It's got 23rd, 24th, 25th. And that is on page 147. And if you look, the leftmost column in the page is called the sun. And so that's going to give us two things. If you look at these two columns, the GHA and the declination. Okay?
So that's how high we would see that. So based upon the time of day,
Mhm.
that's at Greenwich Mean Time, where we would see the sun at.
Well, it's where the sun is located in the sky.
Okay.
Yeah, it's like if you imagine the Earth's latitude and longitude projected on that Greek crystalline sphere in the sky, that's where the sun happens to be. Okay?
Okay.
That's its latitude and longitude. We don't, presumably, we already know kind of how high it is because we just measured it with a sextant.
That's where it would be normal to the surface of the Earth.
It's its latitude and longitude. It's just like it's a sphere in the sky with latitude and longitude. Just we're calling it GHA and declination instead of latitude and longitude. But it's the same concept. It's a coordinate system, and this tells you where it's at.
Make sure you're going to say if it's GMT or UTC.
Well, yeah, this is Greenwich Mean Time, right? So we're only dealing with Greenwich Mean Time. So we're always going to be converting from what our watch says to Greenwich Mean Time.
So it's the sun's position on the Earth.
Right. And it does say in this comment, it used to say years ago GMT, but it says UT now, Universal Time. So just so you know, that was a question so earlier. Now, I'm a person of habit, so I keep calling it GMT. Anyway, so you've got the sun, declination, but it's only for the day and the hour. That's all it is, right? They do this in a way so that you don't have a big giant fat book by telling you every minute of the day, because 1 hour turns out is pretty much like another. So if you go to the back of the page, back of the book a little bit, you'll see a section called Hours and Minutes. Let me see if I can find a page number for that. Oh, I think I went by it. Hang on. They used to make them different colors. It was easier when they did that. They were gray. Okay, let's get past December. Okay, it's called, the pages are called increments and corrections. It's a slightly different color, you know, so if you go back to, well, let's see, I'm going to give you a page number because it's in Roman numerals. But anyway, what that is that's every single minute broken down. Every hour is like another hour. So the sun moves is more or less just as fast 1 hour as it does another. So you've got the days and the hours in the first part for every day and hour of the year, and the second part you've got a typical hour broken out. So when you take the sunshot, it's not likely you took it exactly on the hour. There was some minutes and seconds left over, and you use that table at the back, the increments and corrections, to allow for the amount the sun changed, its GHA, its declination, in that additional number of minutes and seconds from the even hour. So the first part gives you the GHA declination for the even hour, and then the last part, the increments and corrections, gives you the way to interpolate for that part of an hour following that. Okay.
So the value here would be you look up the minutes and then the seconds. And then
Right.
This is how much you add to them.
Right. Well, we'll go into the specifics about it a bit later. But yeah, that's right. You've got it right. Great. So that when you've done that, when you've gotten the GHA and the declination of the sun, you finish that step of find the position of the sun. Okay. Now, the next thing you do, I'm going to describe it this way. You could solve this mathematically by a much more complicated method than what this book does for you. But this thin book allows you, with an economy of space, right, to draw a line of position. And the way it does it is this. It doesn't have the solution worked out for everywhere. It has it worked out for a finite number of spots on the Earth's surface, one of which is near you. And it will tell you what the sextant would have read at one of those spots. And because you're read something different, you're some distance away. It's like this. If you're looking for a specific address and you ask somebody, they could tell you, oh, go to 863 4th Avenue. Or they could say, just go 2 blocks past the 7-Eleven. Okay? One's a very precise thing, the other gives you, you're in the neighborhood, just go 2 blocks, okay, there I am. Okay? So that's what this book does. This book essentially allows you to determine the difference between, or where you're at, based on the difference between what you actually got with your sextant and what the sextant would have read at one of the hypothetical positions. So just like you found the position of the sun, now we are going to find one of those hypothetical positions that's near us. So the first thing you do in the next step, and this is step number 4, you pick an assumed latitude. You're going to have an assumed latitude and an assumed longitude. Now understand, that is not your DR position, your dead reckoning position, the position where you thought you were. That's part of the basic information. It's where you think you are based upon how far you think you've gone and the direction you think you've gone since your last fix. Or maybe it's just what you read off the GPS because you're in a contest with yourself for how close you can get. But whatever the case, that DR position, deduced reckoning position, that's your best guess as to where you're at, and you win a little bit better because that's why you're doing this to begin with. The assumed position is one of those positions from which we're using as a reference point. All the assumed positions have a whole number latitude, either plus or minus. So it's not going to be 32 degrees, 43 minutes north. It's going to be 32 degrees or it's going to be 33 degrees. You're going to pick one of those or between one and the other. It's got to be a whole number, okay? So that actually we can make the process easy. So you pick an assumed latitude. Then you're going to pick an assumed longitude, okay, that in this hemisphere, it's all you'll ever do. In the eastern hemisphere, it'll be an addition thing. But trust me, you're going to get used to just doing this. You pick a longitude, you just pick it, that when you subtract it from the sun's GHA, winds up with a whole number, okay? That difference in longitude between us And the sun's longitude, GHA, is called local hour angle. We want a whole number local hour angle. So we start with the GHA. It's going to be a certain number of degrees, minutes and tenths of a minute. And we're going to pick a longitude that's pretty close to where we think we are, as close as we can get, with the same minutes and tenths of a minute. So when we subtract it, we end up with a whole number. Whole number latitude, whole number local hour angle, okay? That allows us to go into this table, and it allows us to find what the sextant would have read at that assumed latitude and that assumed longitude, okay? The difference between that reading is called an HC. Okay, so we start with an HS. Before we corrected the sextant, we corrected it to an HO. Now we're talking about an HC, which is a hypothetical number. Okay, what the sextant would have read. Our sextant didn't read that, so the difference tells us how far away we are. So first of all, we find an HC, okay, then we have to know what direction from that reference point we're in. That's called the azimuth, okay? That is the direction from that spot to towards or away from the sun, the azimuth. The azimuth is just the bearing to the sun. You know, if we look straight in the sun there, that's the azimuth, okay? So we're going to find that from this book, the azimuth. And then our line of position is perpendicular to the azimuth, either towards or away from the sun from that hypothetical point. How far towards, how far away, kind of depends on the HO. If the HO is bigger than the HC, right, this angle is bigger, it's towards the sun from that point. If it's smaller, it's away. Okay, are your eyes glazed over yet? No, I would thought so. So this whole process, and then the last thing is you plot it out. That's number 9, okay? That's 9 steps, you got the line, okay? Now, this is the foundation for all of this stuff. So it sounds like a lot right now, but really it's from now, for a little while, it's going to be quite repetitive and do the same thing over and over again. Yes, question? Caitlin.
The last numbered step on the portions.
I didn't quite hear that, Caitlin. What was that
So
again?
the last numbered step, and they do 4.
Oh, I'm sorry. So let me go through that again. Yeah. All right, I'm going to go through these, the whole thing again, but I'm not going to go into quite such detail, so you have it all down. So step number 1 is the basic information, okay? Step number 2 is correct the sextant. Step number 3 is find the position of the sun. Step number 4 is pick and assume latitude. So I got you as far as step number 4 while enumerating them. I didn't enumerate the next one, which is pick an assumed longitude. That when you subtract it from the GHA, it gives you a whole number. So 5 is pick that assumed longitude. 6 is find the HC, what the sextant would have read at that place. That's number 6, find the HC. Number 7, get the azimuth of the sun, right? That's called a ZN, that's the notation for that. 8 is get the intercept, that's how far away we are from the sun by comparing what our sextant read and the HC, what the sextant would have read at that position. And so get the intercept, and 9 is plot that all out. Okay? Well, I'm going to go this one more time. Basic information, correct the sextant, find the position of the sun, pick the assumed latitude, pick an assumed longitude, find an HC, get an azimuth, find an intercept, and plot. Right? 1 through 9. Want me to go through it one more time?
Yes.
Okay, number 1, basic information. Number 2, correct the sextant. Number 3, find the position of the sun. Number 4, pick an assumed latitude. Number 5, pick an assumed longitude. Number 6, find the HC. Number 7, find an azimuth. Number 8, find the intercept. Number 9, plot the line of position. Okay, now I told you don't use forms because I think it impedes your internalization of it. It doesn't do that if you just have that list in front of you. Okay, just have the list, right? So, so I'm going to go through it now a little bit more slowly. Okay, we're going to actually open the books and look at them. So first of all, let's go back to the basic information, okay? We're going to write down what day it is. And then we're going to write down the time that we took the observation. Now that's going to be probably a combination of our watch plus the time zone, we're in +7, plus the minutes and seconds when I started it. So if I'm looking at my watch, I might just look at my watch. Or if I tuned into WWV, I started clicking it on the minute, and then I stopped it when I took the observation. What does taking the observation mean? Well, it means that you bring whatever it is you're looking at its image into coincidence with the horizon, okay? If it's a star, it's just this point you're bringing down the horizon. The moon and the sun, though, have diameters. They're like disks. And therefore, it's important to note if you brought the lower edge of the sun or the moon into coincidence with the horizon, or the upper edge. The edges are called limbs. So it's a lower limb or an upper limb. Most people use the lower limb. Particularly in the afternoon, you can have the sun sitting just above the horizon and just wait until it just kisses it, and then click the watch, and then you got the time. Or in the morning, you can have the upper limb of the sun almost to the horizon as it's coming up, and wait until it touches it. And then click your stopwatch or look at your watch. You're looking for the two edges coinciding, but it's important to note if it's lower or upper. You might also only be able to see one edge. Sometimes the moon isn't the entire thing, you know, and sometimes a cloud might occlude the upper part or the lower part of the sun or the moon. So you need to know what the body you shot was, what planet, what star, if it was the moon, if it was the sun, and if it was the lower or the upper limb, okay? You need to write down your dead reckoning position. Where do you think you're at? Because you're picking things that you think are close to you, so you kind of need to know where you think you are. So that's your DR position. You need to write down the time. I think I've said that. I'm starting to repeat myself. So in UT, or universal time, hours, minutes, and seconds. Okay. I think that's it for the basic information. Okay. Oh, your height of eye. You need to know how high up and off the water you are. So, you know, on my boat, it's like 5 feet. On the Star of India, it's like 22 feet or so, right? So how high you are is a big deal. Or it's not a big deal, but it is something you have to do. So that's the basic information. All right. Everybody have that?
We include that in your sensor.
Oh, that's right. Thank you, Bob. So you might have some sextant error. You might have arc error, which we said is usually negligible, or you might have index error. But the index error, that is something you might be able just to take out by adjusting the sextant, okay? But if you don't do that, you look at the horizon and you bring the horizon into alignment, and then if you look at your sextant, and if you're on the arc, right, if you're towards night, if it's 0 point something, you make the subtraction of that amount. If you're off the arc, right, if you're back beyond 0, then you add it, okay? But it's going to be probably close to 0 if you've adjusted your sextant. All right? Okay. Hopefully I got it all. Yes, question?
Is it the height of the sextant from the waterline?
Yeah, more or less. Yes, your height of eye. And you're looking through the sextant, so they're going to be the same thing. Yeah. So if you're on a boat with a little freeboard, you add your own height to it, or where your eye is. Okay? Okay, so that's the basic information. And then you correct the sextant. And again, to correct the sextant, which is step 2, you go to the first pages of the Nautical Almanac. The first thing you correct it for is usually a dip. And so if you look at the page for dip, you'll see that you have meters on one side and feet on the other. And so in the big long column, 8 feet is about the minimum. But if you look over to the right, you'll see other versions, like there's 2, 4, 6, 8, 10. Figure out what the closest is, and it's always going to be, however many feet you are, it's always going to be a negative number. You're going to be subtracting minutes and tenths of a minute from your HS. So you write down your HS, and the first thing you correct is the dip. And I should have said the HS is your also basic information. Now, here's the thing that happens all the time, especially if you're tired. You go through all this trouble, you click it, you got your sextant in your hand, and you kind of want to put that thing in a box before you drop it. And so you go down and you put it in the box and you move the arm and you go, oh, I forgot to write down the HS. Got to do it all again, right? Everybody has done that does this much. So make sure you write it down before you go trying to put the sextant away.
So you said HO is the height of observation?
HO is the corrected value. The sextant is it's the raw number you read right off the sextant. The HO is what you get after you correct the sextant.
Okay, and H stands for what?
Height.
Height?
Just height, yeah, just height.
Okay, so the HS is
Is a raw sextant number.
the height that you're off the water.
It's the angular measurement. You measure the angle of the sun.
Okay.
Degrees, minutes, tenths of a minute. The height is that angle. It would have been nice if they'd have called it something else, but it's an abbreviation and
So it's the angle of the thing we're looking at.
Yeah.
Whatever the number.
Okay.
Yeah,
That it
yeah,
is, okay.
yeah. Whatever the number you read off the sextant, that's the
And
angle we're
then the
thinking.
dip adjusts is what you add or subtract depending on
You
your
only
height.
subtract.
Okay, because
Right.
you're always above.
You're above the horizon. In that your horizon's further away.
Then you
And
subtract
you're,
the dip.
yeah,
Okay.
and then you're not there yet. You haven't got an HO yet, but we have a question.
Is that also what's called the main of the?
No, we're getting to that next, okay? So you've corrected it now for dip. Your next thing to do is correct it for the main correction. And the main correction is a combination of two things. It's the fact that if it's the sun, well, the numbers are all as though you shot the exact center of the sun, but the sun doesn't have a nice convenient little dot in the middle of it, so you shot the upper and lower edge, right? So you didn't actually measure the height of the middle of the sun, it's the edge of the sun. So that's one thing. Another thing is this, is that the light of the sun to get to you has got to go through the atmosphere. If it's coming straight down, it's not refracting at all. But if it's coming at an angle, the light is bending. So that much more than 10 degrees off the horizon, then it's just too low to be accurate. And so what the main correction is a combination of refraction and semi-diameter. And the way you find that one, you go to the page to the left where it says sun, and you're either in October to March, or you're in April to September, one or the other. Currently, we are in April to September. And then you look,
Sorry, what page are you on?
we are on page, right at the first page, yeah. Right where it says altitude correction tables, 10 to 90 degrees, sun, stars, planets. And you're in the sun column. You're not only in the sun column, you're in the sun April to September column. And then you go down the page to a bracket that the dip corrected sextant reading. As you see, they start at about 9 degrees 53 minutes. It goes all the way to 90. So there's two numbers, right? And you have to decide if it's the lower limb or the upper limb. So if it's the lower limb, it's the number immediately to the right, and it's positive. If it's the upper limb, it's the next column over, and it's negative. Okay? Got that?
So the APP altitude, how do you determine that number?
Okay, apparent altitude is the HS after you've corrected it for dip. Right? You've taken the raw sextant number
Okay.
and you've subtracted for dip, and now you've got an apparent altitude.
Okay.
Okay?
So then whatever that number is.
Whatever that number
this
is,
chart.
yeah, you're going to bracket it with these two numbers if you're in the right column. April to September, lower limb or upper limb. Okay? So that's your main correction. So you take the sextant number, you correct it for dip, that's a subtraction. If you then you do the main correction, and that is usually an addition unless you do the upper limb. Okay? And then what you end up with, and then if you've got an index error of some sort, you allow for that. Okay? And what you end up with now is an HO. You corrected the sextant, you completed step 2. Okay? Okay. Number 3, find the position of the sun. Okay? Well, go to the pages in the Nautical Almanac, and let's say, what's today, the 24th? Okay, let's go to July 24th. All right? And July 24th is on page, it's starting to get dark here, so I have to move this along. It's on page 147.
Lights on?
Yeah, well, helpful if we turn the lights on, because you guys can't see any better than I can. Well, many of you can, I know, but I don't see very well. It's getting darker.
So now we're going to look to find where the sun is at local.
We are going to find that, right.
Okay.
Where the sun was when we took that site.
The
Okay?
local noon position of the sun.
Not noon position,
No,
no.
the sun's local noon.
No, we're not trying to find the sun's noon position. We're trying to find the sun's position, just its position, right? Noon is a separate thing that we haven't got to yet. Okay, so if you look, you can see UT, and we go down the road to the left where it says sun for July 23rd, 24th, 25th, Tuesday, Wednesday, Thursday. We're in July 24th, Wednesday, and it starts off with the hours at 00 hours all the way up to 23 hours. So just for the sake of it, let's say at UT it was 19 hours, right? So it was the 24th at 19 hours. And so if we go to 19 and you look over at GHA, you're going to see 103 degrees. Yeah, but I'm still going, I will, because we're going to go through all again. Yeah, because I'm going to do this yet again. So I just want everybody to follow me along with me at this, and then we'll do it where it's in the overhead. So it's, you look at it at 19, it's 103 degrees, 21.8 minutes. That's your GHA for the hour and the minute. Okay, I mean for the hour, excuse me, for the hour and the minute. For the day and the hour, it's 103 degrees, 21.8 minutes. Okay, is everybody seeing something like that?
Yes.
Okay. Slip to the right, and you'll see in the declination column that at 19 hours, the declination was north 19 degrees, 38.0 minutes. Everybody see that? It's in the same line as the, right? That's the declination. So you found for the hour, the almost, you haven't done it quite yet, but you found for the hour the GHA and the declination.
And the declination always would be between the Tropic Cancer and Tropic of...
Yep.
Okay.
Yep, it will always be in the tropics somewhere, north or south. It doesn't get beyond 23 and a third degrees, north or south. So we've got that. There's one little thing you're going to do, and you're going to drop down to the bottom of that column, and you see a little number says D. D, that's an interpolation factor. That's what D usually is. It's a 0.5. What that tells you is that the sun's declination is either increasing or decreasing by that amount each hour. Okay? Now, if you look at the declination numbers, you'll see that they are going down. So, and if you look each hour, they're dropping by about half a minute, right? So that little D factor is negative 0.5. Just write it down, and you're going to use it later. Okay, so I said it was 19 hours, and how many minutes did I say it was? I just made something up. Was it
21.8.
21 minutes?
21.8.
Oh, 21 minutes, 28 seconds.
Yeah.
We don't have point of a minute.
GHA was 103, 21.8.
All right, that's the GHA, but the time we took it was 19 hours.
19 hours, yes.
19 hours, let's say it was 43 minutes and 10 seconds. Okay, somebody write that down. So 19 hours, 43 minutes and 10 seconds. So let's go back to the increments and corrections pages to the page for 43 minutes. Did I say 43 minutes?
Yes, 43.
Okay, 43 minutes. So find that in increments of corrections, 43 minutes, and you'll see that there's 3 columns, one for the sun and the planets, one for Aries, and one for the moon. So 43 minutes, and how many seconds did I say?
10.
10 seconds. So when I go down here, what I find is in sun and planets, on the column for 43 minutes, I'm going to find 10 degrees, 47.5 minutes. Okay, 10 degrees, 47.5 minutes.
Okay, so I see on the top there,
Okay.
each one of these is minutes. I want to find.
Right, you're always going to add that.
So the 43
Right.
m
So the minutes,
and 10 seconds.
so the minutes and seconds correction always gets added to the GHA, right? And you to turn it into a GHA. Okay, one last little thing. Remember that little D number of 0.5? Okay. If you go immediately to the right, you'll see a column that says V or D correction. And at 0.5, we have a correction to our declination of 0.4. Right? It's decreasing, so we subtract 4/10 of a minute from the declination. Okay? Don't worry if you're lost, okay? Because we're going to go through an actual problem again after this. But now we've got the declination, okay? All right. So we've completed that step. We found the position of the sun. Okay? Now, step 4 is we pick an assumed latitude. 33 degrees sounds nice to me. You guys like that? Okay, 33 degrees. All right, that's our assumed latitude. Now we're going to pick an assumed longitude, and when we subtract it from that GHA, gives us the whole number. So what was that GHA again? Can someone tell me? After we added the minutes and seconds? What was it? 103 degrees, 21.8 minutes? Okay, 103 degrees, 21.8? Okay, so if it's 103 degrees, 21.8, we got a little bit of a problem because that is, we can't subtract our longitude from that without getting a negative number. What do we do then? We add 360 to it. Yes?
That 102.21.8 does not include the addition of the increments.
Oh, add the increments and corrections, yeah. What does that give us?
So it's the sum of those two numbers together.
Right, right. And so what do we have?
114.09.3.
Okay, 114.09.3. Okay. The problem is we're 117 something, aren't we? And you can't have a negative number here. So what do we do when we have that problem? Well, add 360 to it. You go all the way around the circle and come back again. So take that number that Bob just said, add 360 to it.
This is my math is correct.
And Bob's math is correct. But we're not going to quibble too much about that. So what was that number, Bob? Once again?
It was 113 and 79.
Okay.
69.6.
So that's 473 degrees and what? 473 degrees and some odd minutes into it.
And carry the 1 for the 13.
Okay, all right.
Was this in,
114,
It's in
9.3.
I'm sorry, there's two. One more time. Your question? No, we're not dealing with seconds in this minute. Only in time are we talking about seconds. Minutes and tenths of a minute. So when you add the 360 degrees, it's 473. 473, and then minutes and seconds. What is it? 16 minutes, 9 seconds. I'm sorry, 16 minutes, 16.9 minutes.
If it's point, that's a real decimal, and you subtract the minutes, the degrees from it, then you multiply by 60.
Well, let's not. Yeah, but we for the GHA we knew what the minutes and tenths of a minute were. So what was left over? What was the minutes and tenths of a minute?
Can we pull up the whiteboard so that we
Well, I'm going to do that. We're not. No, not yet. I'll get to that. Can someone just tell me what the minutes and tenths of a minute were? Well, Bob was adding it up. People, you guys were adding them up.
There was 113 114 degrees and 9.3 minutes.
9.3 minutes. Okay, 114 degrees. 9.3. So we had 9.3 minutes left over, right? So whatever we pick for assumed longitude is going to end in 9.3. So if it was 100, so basically if we're at 117, it's 117 degrees, 9.3 minutes. That's the number that we subtract from that big LHA after we added 360 to it. And what we have left over from that is a local hour angle. Okay, with a whole number. Okay.
Also, your PR longitude.
What was the deal? Oh, I just made this whole thing up, so I don't know. Now we're going to work out a real one. So basically, I've got us to that point where we go into this book. But that's about as far as I want to go with made up stuff. So we're going to use an actual site here. Okay. So, but I wanted to go through that so that we leave, so that then when we go through it now, it'll be a repetition of our first effort. So, people looking stuff up for me. Okay. So you guys will want to write down this basic information. Okay. This was July 20th, 2024. Well, why did it not stay on? Okay. Now here's my experiment here. Is that showing up? Okay. Okay, this is the sun. LL, lower limb. Okay? Our DR position 32 degrees. Can you see that?
Yeah.
Okay. Okay, our DRPS is 32 degrees, 40.3 minutes north. It was 117 degrees, 13 minutes west. Okay. Height of eye, and a little symbol for that is often looks like that. It's like a little eyeball here. Okay, so height of eye, I'm going to say is 6 feet. Okay? 6 feet. We're 6 feet off the water. 6 feet. Okay? All right. So the time that we took the site was, I'm going to say, let's see this. Local mean time was 13 hours, 00 minutes, okay, 00 seconds when I got the beep from WWV. The minutes and seconds in addition to that, which is M and S, okay, is 5 minutes. Right here. .41 seconds, which gives us local mean time with our time zone, we're at +7. So our UT is 20 hours, 5 minutes, 41 seconds. Okay? All right, well, that is our basic information. Okay, so the next step, sorry, the next step is, there is one element of basic information yet. We actually have to have the HS. So, what did the sex read? So, HS was 77 degrees, 18.0 minutes. Okay. Okay, so that was the HS. Okay, so our next step is going to be to correct the sextant, isn't it? All right, so we have a dip correction. Someone want to look up and tell me what that would be for 60? Well, yeah, but you'll see a little column that it has 2, 4, 6, and so on. I don't know why they do it that way, it's confusing, but there you go.
2.4 minus 2.4.
Minus 2.4, okay.
4 minutes.
You know, I'm gonna say it's sorry. I'm gonna say it's 5 feet. Height of is 5 feet. So that's minus. Sorry. That's at 5 feet. That is going to be minus 2.2, I think, right? Minus 2.2. Well, because I've already worked this out, and because I used 5 feet, I forgot I'd use 5 feet instead of 6. So my fault on that. So at 5 feet, you know, and it's that's halfway between the 4 and the 6 in your little table. So I use 2.2. Okay.
I don't think I'm looking in the right spot.
Okay. So let's go to the nautical almanac. Let's go to the first pages. Right. There isn't 5 feet. What there is, though, is there's 4 feet and 6 feet. So if you look at the dip column, and you go all the way to the right, and you go down to where it says feet, it goes 2, 4, 6, 8, 10. So 4 feet is minus 1.9. 5 feet is minus 2.4, so I picked 2.2 because, you know, it kind of splits the difference at 5 feet. Okay? 2.2. Okay, so the next one, so let's go ahead and do that subtraction. We take 2.2. Make sure I get the right one.
Minus 2.2 minutes.
Yeah, minus 2.2 minutes, that's 77 degrees, that's 15.8, isn't it?
77.
15.8 minutes. Now, we need to apply the main correction. Okay? So, we're on the same page, we're still at the front of the book. We go to where it says April to September, which is the season we're in. And we look for an apparent altitude, and our apparent altitude at this point is 77 degrees, 15.8 minutes. And we run down the column till we bracket this. And it looks to me like it's 15.7. Is that what you guys are getting? Yeah. 15.7. And it's positive. So look where it says April to September, where it says degrees and minutes, and go down this column to the left until you have bracketed our actual apparent altitude.
And our apparent altitude is 77 degrees, 15.8 minutes.
Yes, that's right. Because we subtracted the dip from our HS. Now, okay, we're going to add in the main correction, and the main correction symbol is usually a circle with a dot in it. So the main correction is 15.7 I have. Is everybody getting that?
15.7 minutes.
15.7 minutes. So, 8 and 7 is 15. 6, 1, 5 is 11. 3 minutes. So it's 77 degrees, and that is our HO. Right? Our observed altitude. Okay? It added 15.7 minutes to give us an HO of 77 degrees, 31.5 minutes. Okay? I'm sorry, what?
It was 0.8 and 0.7.
Yeah, so you have to carry one over, that makes it 30, that makes it 31. Okay, now what we do is we have to do what? We have to go to the next step, which pick an assumed latitude. And remember, our DR position was 32 degrees 40.3 north. So our assumed latitude, well, you know, I'm going to say 33. We're going to be using that a lot, probably, because we're going to be using actual live sites. So assumed latitude 33 degrees north. Okay. So you know, actually, sorry, it's late. Forget what I just said. I just got jumped ahead of things here. We're correcting the sextant. Now we have to find. The position of the sun. Don't we? Sorry about that. I got ahead of myself. Okay, so let's go back to the pages for July 21st, or July 20th, 2024, and go to 20 hours. July 20th, 2024, right, which is Saturday, and right, you look up the UT, and it's 20 hours. You go down to 20 hours. And at 20 hours under GHA, you find 118 degrees, 23.4 minutes. Is everybody finding that?
118. What?
118 Wait a minute, let me make sure I'm reading this right. Yeah, 118.23.4. So I'm going to write down the little letters GHA, the letter GHA. One 18.23.4. Okay, so that's the GHA. I'm going to come over here and write declination, and in the same row that I found the 118 degrees, I'm going to go over and write down north 20 degrees, 26.7.
This comes out of the same table.
Same table, just go immediately to the right, and you'll see 20 degrees, 26.7. Okay? I'm going to do one more thing before I leave this page. I'm going to drop down. No, just the sun. Go to the sun page. Just the sun. So the little d in the bottom is still 0.5, which means it's decreasing by 0.5 of a minute each hour, and it's decreasing, right? The sun's going down a bit lower each day. So I'm going to write little d down here. Little d equals negative 0.5. Okay? So I found the GHA and the declination for the day, the 20th, and the hour, 20 hours. But I've got this 5 minutes and 41 seconds still to allow for it. Okay? So, because the sun has moved in that time, in that 5 minutes, 24 seconds, I go to the increments and corrections page for 5 minutes. Okay? 5 minutes, and you'll see in the 5 minutes, you'll see sun and planets, Aries and moon, it's sun and planet shows and forth. So go to the 5 minute column, okay? And you've got 5 minutes and 41 seconds to allow for. So go to 5 minutes and drop down to 41 seconds. And what you should see under sun and planets at 5 minutes, 41 seconds is 1 degree, 25.3 minutes. 1 degree, 25.3 minutes. That's always additive. 1 degree, 25.3 minutes. Okay? So that is 0.7. 23 and 25 is 48. So 48.7 minutes, 119 degrees. 48.7 minutes. Okay, that is the capital letters GHA. Now, for the declination is changing by 0.5 of a minute each hour. So for the part of the hour we're in at 4 minutes, if you look at the V or D correction for 0.5, it's 0. So for all practical purposes, the declination hasn't changed. Right? It's this number right here. So cross that out and put declination. So declination is north 20 degrees, 26.7 minutes. GHA is 119 degrees, 48.7 minutes. Okay? So we have found the position of the sun. Now, a minute ago I got ahead of myself. I had us pick the assumed latitude. Let's go ahead and do that now. So, I'll just write over here, AL equals 33 degrees north. Okay? Because that's the closest whole number latitude to 32 degrees, 40.3 minutes, which is where we think we are. Okay? Now, we're going to have to pick an assumed longitude that when we subtract from this winds up with a whole number. Now the symbol for longitude is lambda, that number there. And if you look at our chart, we're at 117 something, I think, aren't we? Okay, so for 117 something, let me just make sure I'm on track for what I'm supposed to be here. Okay, 117 degrees, 48.7 minutes. And we do the subtraction. So that's our assumed longitude, that's our assumed latitude, So our LHA, local hour angle, is just 2 degrees even. That's got to be a whole number, 2 degrees of the LHA. So now we have gone through the steps we've gone through. We've found the position of the sun. We picked an assumed latitude. We've picked an assumed longitude. And we've got an LHA. So we're done with the nautical almanac for now. So, unless we want to do another site. And we go to the 249 tables, okay? And the way they're organized is, if you just open it up to any page, what you'll see is latitudes across the top of the page, right? This has for latitude 0 to 40 degrees. So if you're anywhere between 0 to 40 degrees, you're good. Now we picked a latitude of 33 degrees, didn't we? Okay, you're going to be ending up using this page a lot since we're using sites locally. So go to latitude 33 degrees. And understand what we're trying to find now is what the sextant would have read at exactly 33 degrees north and 1:17:48 minutes west. So we go to latitude 33 degrees. And now, we're zeroing in on one set of tiny numbers on this page. So, the declination is either 0 to 14 degrees, or it's larger than that. It's 15 to 29 degrees, okay? Now, in our case, our declination is what? Our declination is 20 degrees. So we're in the section that says 15 to 29 degrees. And our declination is the same name as our latitude, not the contrary name. So the page we're on is latitude 33 degrees, declination 15 to 29 degrees, same name as latitude. So there's about 6 of these latitude 33 degree pages. We got to find the right one. So 33 degrees, declination 15 to 29, same name as latitude. Okay? Okay, so now we're on the right page. Now we've got to find out what the sextant would have read at that spot. And to do that, we've got to find the declination of the sun, which is the column across the top, or we've got to find the LHA. Now the LHA is just 2, right? 2 degrees. So if we look over to the left, we'll see LHA of 2. And our declination, well, our declination is not a whole number, but it only has whole numbers in this column. So we're going to cross-index the declination of 20 degrees with 2, right? Tiny numbers. And we get, that's about the 3rd row down. I reckon it's, looking at my poor eyesight, 76 degrees, 53 minutes. Right? So we have an HC, 76 degrees, 53 minutes. HC is 76 degrees, 53 minutes. Okay? Now, here's where it tells you if you really messed up or not. If these two numbers, the HO and the HC, are really far apart, it's not so good. Okay? They shouldn't be more than 8 degrees apart. If they are, either you picked the wrong assumed longitude or your DR was off by a lot. So HC 76 degrees, 53 minutes. Now we also have, because we have some leftover minutes of declination, we've got another one of those little D numbers. So if we go over there with 2, we cross the row over at 20 degrees, we find a D of minus what? Is it 50? Is it 60? It's 59, minus 59. Okay, minus 59. So that's an interpolation number again. So
It's a plus and a plus.
oh, it's plus, yeah. So D equals plus 59. Okay? So that's going to alter the HC by a certain amount. Before we leave the page, though, we do one last thing. We stay in the same row, and if you see the number says Z, Z is 174. No, wait a minute. Is that right? 172. Okay. Is it? Is Z 172?
172.
So we're going, we're going 20 with, 172. I got it. Yeah, there we go. Okay, yeah, thank you. 20 with, 20 and 2 is 172. So we write the z number down. Z equals 172 degrees. That's not quite the azimuth of the sun yet, but we're getting close. Okay, so we've kind of found the azimuth, we've kind of found the HC. We need to do a couple more things to really get there. So this z number is a raw number, and the way that we turn it into an actual azimuth is, if you look at the top left of the page, you'll see where it says in north latitude, if the LHA is greater than 180, Zn equals Z. And you don't have to do anything. You've already got the azimuth. But if the LHA is less than 180, which it is, you're going to have to subtract that number from 360 to get the azimuth. See that little equation up there? Okay. So we subtract, we put 360. So this is,
182 or 188.
yeah, equals Zn. Okay, that's the azimuth. That is the bearing of the sun from the HC. Okay, so now the very last thing we got to do is find the final HC to get the HC. And so that requires, we look up, it used to be a page that came out, but there's a table 5 here someplace.
Is that the last page?
Is it table 5's last page? Okay. Yes, okay, table 5, corrections to the calculated altitudes. So go to table 5, and what's that about? Well, it's because the declination that we had this extra 26.7 minutes attached to it. Okay, each increase of a degree in declination is increasing by 59 minutes. So almost a whole degree per degree. So we have 26.7, call it 27. So 27, and we cross-index that with 59. It doesn't matter whether you go across the top or across the bottom. So, but 27 with 59 gets you 27. Okay?
Can you do that one more time?
Yeah. So go to table 5. Okay, and table 5 has 2 things that you're cross-indexing. One of them is this little d number that we wrote down of 59. And one of them is this leftover minutes of declination, 26.7. Let's just call it 27. Let's round it. So we've got 27 cross-indexed with 59, and you end up with it, and it's plus. So you end up with 27 here. So you end up with an HC of 76 degrees, 80 minutes, which is the same as 77 degrees, 20 minutes. Well, 80 minutes, you can't have 80 minutes in a degree. Okay? So 80 minutes is the same as add another degree over here and make it 20 minutes. Carry the one, right? So what we did was, again, we had these leftover minutes of declination, 26.7, we rounded it to 27, we crossed-indexed it with a d number of 59, that gave us a correction of 27 minutes, which we added to the HC, that gave us 76 degrees, really 77 degrees, 20 minutes. Okay? What? No, don't need a form, we just need repetition. So now we found the HC, final HC. So now, what we got to do is find out the intercept. How far away towards the way of the sun are we from this? So our HO is 7731.5, HC is 7720. So if we take the HO, 77 degrees from there, 31.5 minutes. From that we subtract the HC of 77 degrees, 20 minutes. We end up with a difference of 11.5 minutes. That's 11.5 miles. Are we towards or away from the sun from that? Well, if our HO is bigger, we are towards the sun. So imagine that you've got this spot on the earth. Here's the sun, right here. And here's the HC. Here's the HO.
You move that up a bit.
That's a bigger angle. As you move towards the sun, the angle gets bigger. So we're 11.5 miles towards the sun. Okay, so I've got this really faint chart here. I'm not gonna try and plot on, but I'm gonna actually kind of fake it here. So what do you do when you plot it? Okay, let me get another sheet. With that, we have worked out the site. We've got the azimuth, and we've got the intercept. Okay, so what do we do? Okay, we go to our chart, our plotting sheet. And on the chart, we go to 33 degrees north. And for our assumed longitude, we go to 117 degrees. What was that?
48.7.
Okay, 48.7, thank you. 48.7 minutes. Okay? Now, that is our assumed position. Not our DR position, our assumed position. And now we need to know the direction of the sun, Zn. Zn is 188 degrees, did I say? Okay. Well, if 180 degrees is down here, 188 degrees is almost, as you can see, I'm just kind of, so I presumably measured this off from the compass rose at 188 degrees, okay? So, here's our assumed position. That's the direction of the sun. Our intercept, our line of position, is perpendicular to this line, and it is exactly, or it is, I'm not going to say exact, it's 11.5 miles from here to here, so we measure 11.5, and the perpendicular line to that is our LOP at whatever time it was we said it was. Anyway, that's our line of position. That's one line of position. Okay, and so you're saying to yourself, you mean I went through all that just to get a line of position, and I don't know where on that line I am? This is just crazy. Well, yeah, it kind of is, but then again, what else you gotta do? You got lots of time on your hands, right? So that's the direction of the sun. But just be patient, wait a while, an hour and a half or so. Instead of the sun being here, it's moved around over to here. And then you do that shot, and then that's a different azimuth, that's a different line of position, and that will cross that first line of position. And where it does, if you haven't moved any, that's where you're at. If you have moved some, well, you got to advance that first line, the direction you think you want, the distance. Okay? All right, that was all easy, wasn't it?
Yeah, absolutely. Clear as mud.
Okay. Well, you wrote that all down. So here's what I want you to do. I want you, first of all, to do two things. This is homework. So your second site that you're going to try and work out and bring in is going to be the same day. Okay? Same day. Yeah, it's July 20th, sun, lower limb. Okay, same DR position, didn't move any. Same lack of index error for the sextant. So sun, lower limb, height of eye, same height of eye, 5 feet.